Okay, hi everyone, I'm Christine, this is Darren and Chris. So here is our song player. We have 4 different songs that we can play. First we'll just go through the features that each of us implemented. So the ones that I implemented were chord playing, also the enhanced note display, and also the graphics.
The features that I implemented were harmonics, dynamics, amplitude modulation, and also multiple instruments.
And I implemented echo, playback control, and a lot of top-level design stuff.
Okay, so first to talk about how we implemented chords. We stored our songs in synthesizable music file formats, and we read in each note one at a time. We read in the note duration and also the note number, or we read in a time advance step. So as long as we were reading in notes, we assigned each of them to a free note player. We had 3 different note players so that each chord that we played could consist of up to 3 notes. And we selected a free note player using a multiplexer with don't care so that the note would be assigned to only 1 note player at a time. And then when we read in a time advance step, we stopped incrementing the lookup address in ROM, waited for time to advance for the specified number of beats while playing the notes, and then once that was finished, we continued incrementing the address and looking up new notes. So here is Final Countdown.
Cool. Chris, you want to talk?
Alright, so the next part of our design is our playback control. Move to the next one. So this is basically something playing only. So I'll be fast forwarding now. So it has fast forwarded. And now I'll be rewinding. I'll play again. So the whole premise of playback control is that when we're in fast forward and rewind mode, we force the durations to be 4. And if we're in rewind mode, we decrease the address and the address has to become 0. And so, and basically, as you fast forward and rewind, you get, if you play again, it'll go back to where it was originally. Another feature that we implemented was called echo. So the basic premise of echo was that we would store a sample for a certain period of time for delay. Say if you want to delay it 100 milliseconds, we store that sample in that RAM. And then after 100 milliseconds later, we would take the original wave and the wave that was stored in the RAM, add it together and output them out. We control this by pulling the DIP switch up 1 and increasing the amplitude by this button and increasing the phase shift by this button. And then if we want to play again, then we just push the switch down again and play. So one design issue that we had was that the RAM could only be such a small size because of memory constraints, so we were only able to have 100 microsecond echo. But it's somewhat noticeable, but here's the song. Oh, really? Yeah.
The songs were fun to write. Took a long time. Okay, so some of the features I implemented were harmonics, dynamics, amplitude modulation, multiple instruments. So harmonics was pretty straightforward. We took a sample, fed it into the frequency ROM, and that would spit out the fundamental. Then we multiplied the fundamental by 2 through 8 to generate 8 harmonics total. And based on the instrument traits, we would modulate those harmonics by shifting them by certain values. And then as you can see, you can get harmonics which are not really perfect sine waves. Right, so that was pretty straightforward. The dynamics was a little more tricky. I actually wrote an ADSR module. I had to rewrite it 3 times. Initially we had problems with resolution when we wanted to attack linearly and decay exponentially. So what we did in the end was we had a a ROM that had exponentially decaying values, and we would increment one address in the ROM every beat, which is barely perceptible by the human ear. And we also had issues translating it from simulation to hardware, and we discovered that the issue was that we had a generate next sample in the flip-flop, which isn't the way it really works in hardware. So once we took out that generate next sample, you can actually see that dynamics being implemented here. As you can see, the sine wave slowly decaying. Finally, for the instrument select, we had a 2-bit instrument select in the song ROM right after the amplitude values, and that would feed into the mux with instrument trace. So we had 4 inputs. There was a woodwind, there was a flute, there was a piano, and there was string instruments. So we simulated those by making a MATLAB script, but they weren't always accurate, so we had to do a little bit of research plus a little bit of tinkering ourselves. For instance, we found that a woodwind only added up odd harmonics, but we also had to adjust the values of those slightly to get it to sound like a real woodwind. Enjoy the rest of the song.
Okay, so next I'll talk about some of the graphics features. First of all, at the top of the screen, you can see 5 different chords being displayed. The middle one corresponds to the chord that's currently playing. To the left and right are the past and future chords respectively. And then on the 2 sides are the past chord and the future chord. So pretty much the backbone behind how this was implemented was by using 5 flip-flops, 1 for each chord. And besides for the future chord flip-flop, the input to each flip-flop was the output from the flip-flop 1 chord into the future. And then in real time, when a chord is finished playing, all the flip-flops are enabled so that each chord cascades down by 1. And then also when that happens, the pretty much brains of the future chord flip-flop are enabled to start working, and we have a separate module for this called Future Song Reader, and it looks into the ROM at future addresses for the future chord, and it also uses logic based on what notes from previous chords should still be playing to determine what that chord should be and assign it to the future chord flip-flop, and finally enable that flip-flop to switch, which ends up happening 5 clock cycles after the other ones have switched. So you can see that working. Then to convert the notes to characters, we use logic to convert each note to its 3-character representation, and then looked up those characters in a read-only memory module which contained 8x8 bitmaps for each character, and finally used that to create a bitmap for the entire screen that can be fed to the raster display when it asks for color information at each XY value. And then other graphics features were that we displayed the 4 names of the songs and highlighted the one that's currently playing. Then finally, for Gangnam Style, we have a little extra kick. So first of all, I'll talk about images. In order to display images, we use MATLAB to create bitmaps for images from the Gangnam Style music video, or animation of it. So we converted those images into 100 by 100 pixel bitmaps. Initially, we had better resolution, but due to memory constraints of our FPGA board, we had to decrease the resolution. And again, we use that to create an overall bitmap for the entire screen. So now, Gangnam Style. We have some additional pictures and also a little bit of animation.
So enjoy the rest of the song.
Yeah.
So finally, we'd like to thank Professor Mitra and all the TAs and section leaders from EE108A. It was a great experience, even though we talked a lot about it in this lab. So thanks, guys.
Clark.
Yeah, I think medicine for everybody.
Yeah, thanks, Benson.
Yay!